This video is about graphing logarithmic equations, and the slideshow was made by Mrs. Casey, and she really likes Harry Potter, so that's something that you may or may not want to know. I've never seen any of the movies or watched any of the books or um, seen a book or watched a movie or whatever you're supposed to say for those words. Anyway, the parent functions, these are things that you learned about in Honors Algebra 2, so this is not something that's new. Y equals log base 2 of x, y equals natural log of x are generic functions for this. The defining points, if you substitute in 1 for x, you will get 0. If you substitute 2 in for x, you will get 1. And if you substitute in 1/2 for x, you will get -1. That's because if we remember, the log is basically the inverse operation of the exponential function. So if I take this equation and I rewrite it, I could rewrite it as x equals 2 to the y. So this is the inverse function. Logs are the inverse function of the exponential function. The domain of a log function, the generic parent log function, the domain is 0 to infinity, and the range is -infinity to infinity. And you can see that by looking at the inverse function, because there's nothing for y that can't happen. Like you can put anything in for y, but x has to be non-negative. Actually, it has to be positive because there's no way that this can be 0 or negative. For natural log of x, just a reminder that the natural log function is log base e. We normally don't write it as log base e, and we never write it as natural log base e. Natural log means log base e, so we don't need to write it like that. So the defining points for this one, if I substitute in 1, I get 0. And that's true of any log function. If I substitute 1 in for x, I would get 0. If I substitute in e, I get 1. And if I substitute in 1 over e, I get -1. Again, the domain is negative or 0 to infinity, and the range is -infinity to infinity. If I wrote this inversely, the inverse function of this, if I just kind of figured out how to rewrite this, I would write x equals e to the y. So these two things have the exact same points because a log function is really the inverse of an exponential function. So I just have to be really careful in how I speak about this, though. These two functions, log base 2 of x equals y and x equals 2 to the y, are not inverses in and of themselves. These actually graph the exact same thing. So these two things graph the exact same thing, but the inverse function of a log is an exponential because those kind of go back and forth. And if you had y equals the natural log of x and you wanted to undo something, or for example, let's say you had 3 equals the natural log of x and you wanted to solve the equation for x, you would take e to both sides, and e to the natural log of x basically cancels each other out. That's why they're inverses. So x would equal e to the third in that case. Okay, so now let's talk about graphing these functions. So the coordinates of the defining points are 1/2 -1, 1 0, and 2 1, as we wrote here. And you could see that if you were looking, for example, log base 2 of 2 is 1. Log base 2 of 1/2 is -1. These are things that we've learned so far. So I can plot these points, 1 0, 2 1. If I wanted to plot 4 2, I also could, because log base 2 of 4 is 2. And then I have 1/2 -1. My asymptote is going to be at 0. And then I could graph my log function. So log functions approach the asymptote vertically, and then they grow really slow after that. So now if I'm going to graph natural log, 1/e, -1, 1, 0, and e1. How do I graph e? Well, e is a little bit less than 3. It's about 2.7. So if you think about it on a graph like it's a little bit less than 3, that should really help you. So 1, 0, e comma 1 is about 2.7 comma 1, so it's a little bit less than 3. And then 1/e -1, since e is around 3, that would be about 1/3 -1. So I can approach the graph somewhat like that. And then I can graph my asymptote just to make sure everybody that's grading it would know that it never hits the y-axis. Okay, let's do a few more of these. So log base 3 of x. So if I'm thinking about the defining points of log base 3 would have defining points 1, 0, 3, 1, and 1/3 -1. So if I have a horizontal reflection, what that's going to do is that is going to flip all of my x values to be negative. So 1/3 -1/3 -1, -1, 0, and -3, 1 would be my new defining points. So -1, 0, -3, 1, -1/3 -1. It's going to look something like that. And so if I analyze this situation, I would have the domain is -infinity to 0, and the range is still -infinity to infinity. Number 4, f of x is 2 natural log of x. So essentially what's happening is I'm having a vertical stretch of 2 to all of my original points. So my original points were 1/e -1, 1, 0, and e1. Well, all of the y values are now going to get multiplied by 2. So I have 1/e -2, 1, 0, and e2. So now I can plot these points on the graph. Remember that e is around 3, so 1/e would be around 1/3, 1/3-ish, -2, 1, 0, and e, which is around 2.7, comma 2. So notice that this graph is just getting stretched vertically by a power of 2, or by a factor of 2. This does not change my domain and range at all. So if I multiply the range of an exponential function by 2, that doesn't really change anything, because -infinity to infinity times 2 does nothing to that. Number 5, f of x equals negative log base 2 of -x. So this has a vertical reflection and a horizontal reflection. So if we take a look at the original points of log base 2 are 1/2 -1, 1, 0, and 2, 1. So notice I have both x and y getting reflected. So it will be -1/2, comma +1, -1, 0, and -2, -1. So everything kind of gets flipped. So -1/2, 1, -1, 0, and -2, -1. So what's going to happen is this graph, if I wanted to plot one more point, remember that an original point would be 4, 2. So if I was going to transform that, it would get transformed to -4, -2. So -4, -2 could be another point. And that may help you see what the graph is doing. I've had both a horizontal and a vertical reflection. So what that means is my domain is now going to be -infinity to 0. My range is still -infinity to infinity, but it's a little strange in the sense of looking at what a log function looks like, because it's growing slow, but growing slow going to the left. I know that is kind of weird because normally when we think of growing, we're thinking going to the right. But this function ends up kind of flipping both this way and this way from the original function, which would look something like this. So it flips both horizontally and vertically. F of x equals -1/2 natural log of x. So my original points are 1 over e, -1, 1, 0, and e, 1. So what happens is all of my y values get multiplied by -1/2. So I have 1 over e, 1/2, 1, 0, and e, -1/2. So all my y values get multiplied by -1/2. So if I plot these, I have 1, 0 on the graph. I have e, which is around 2.7, -1/2, and around 1/3, 1/2. So this function got flipped vertically, vertical flip, that's the negative up here, and a vertical stretch of 1/2. So notice that the graph goes this way, and it kind of elongates how far it takes in order to get somewhere. The domain, still 0 to infinity because nothing changed with the x values, everything was vertical. And then I have -infinity to infinity. Two more of these to do together. Number 7, I have log base 4. So let's quickly write the points down. That would be 1/4, -1, 1, 0, and 4, 1. So what's happening to all of these? My vertical stuff, I have a vertical stretch of 2. So I multiply all my y values by 2, and I flip the signs of all my y values. So in that case, the first one would be -1 times -2, basically. So that becomes 2. 0 stays the same because 0 times -2 is still 0. And then 1 times -2 is -2. All my x values get stretched by 3. So all my, remember dividing here actually stretches it instead of shrinking it. So that means all my x values get multiplied by 3. So 3/4, 3, and 12. So 3/4, comma 2, 3, comma 0, and 12, comma -2. That's going to be way over here. So I can graph this. I know that went way over something, but the domain of this function is 0 to infinity, and the range of this function is -infinity to infinity. Okay, now if I look at this, I get a vertical flip. So I would multiply by -1 for the y values, and then I would add 1 to the y values. Whereas with the x values, I'm going to move it to the right 4, so add 4 to the x values, because this is a horizontal transformation of 4. So my original points for log base 2 are 1/2, -1, 1, 0, and 2, 1. So I'm just going to add 4 to all the x values. So 1/2 plus 4 is 4.5, or 9/2. 1 plus 4 is 5. 2 plus 4 is 6. And then For the y's, I multiply them all by -1 and then add 1. So -1 times -1 is 1, plus 1 is 2. 0 times -1 is 0, plus 1 is 1. And 1 times -1 is -1, plus 1 is 0. So I have these points on the graph, 4.5, 2, 5, 1, 6, 0. And so what I'm going to notice is that my new asymptote is at x equals 4. And that makes sense that my domain is now 4 to infinity, because notice that my typical domain of 0 to infinity got moved to the right 4. Then my range is still going to be -infinity to infinity. And it's going to grow. It's basically flipped over from what my typical log graph is, so it looks like this.